Previously, we used theorem 5.19 to solve the problem of finding the least squares approximation of the square root function by this quadratic function. Okay, so this video is mainly focused on going into more detail about why this formula for the approximating function g works to solve these kinds of problems. Okay, so suppose V is a vector space. And so let's simplify things a little bit and think of W as a one-dimensional subspace. Okay, so the problem is the least squares problem, right? So given a vector in V, we want to find x in W such that it's the least squares approximation, right? So that the norm of V minus x squared is minimized. But one thing you should notice is that minimizing this is the same as minimizing the norm of the difference without the square, right? Because basically this is just the distance between V and x and this is the square distance, right? So minimizing the distance between two things is the same as minimizing the square distance. Okay, so if we can minimize this, then we'll automatically minimize this, and so this is what we're going to look for, right? So let's try to visualize things geometrically, right? So W is a one-dimensional subspace, so that's just a line, and let's say W has a unit vector as its basis vector, right? So W1 is a unit vector in W, right? So let's say this is W1. Okay, so and V is a vector in V, right? So V could be pointing in any other direction, right? So let's say this is V. Okay, so what does it mean to find this vector x that's in the vector space W and such that the distance is minimized with V, right? So the distance to V is just taking the points along W and trying to find the one that's closest to the tip of my vector V, right? So let's say I'm at this point in W. It's the distance to V is here, right? So now if I'm here on W and I move in this direction, then I'm getting farther from V, right? So to get the shortest distance, I want to move in this direction. So here I'm getting closer and closer and closer to V until I get to right about here. And then if I keep going in this direction, now you can see I'm getting farther and farther away from V. Right, so the closest point to V happens to be this point here, where it makes a right triangle like this. And we've actually already seen what this thing actually is geometrically. It's just the vector projection, right? So this, like the x that I want, is just the projection of V onto W1. But how do we calculate the vector projection? It's calculated exactly like this. And this is why I wanted to take a unit vector for W1 instead of any other vector for along W. Right, so W is a unit vector, so that means that the length of W is 1, but the length of W squared is just the inner product of W with itself. Right, so this thing is equal to 1. So if this thing is equal to 1, then this is just, the denominator is 1, right? So, and this is just the inner product of V against W1, scalar multiplying W1. Okay, so this is when W is one-dimensional. But now, for a general finite dimensional W, right? So now say W is any other finite dimensional subspace. It is essentially follows from this idea, right? So I can't really visualize W, but imagine this is my subspace W. I'm representing it as a plane, but again, this is not really representing it visually, but we want to somehow picture essentially what's going on, right? So I have my vector V again, and so solving the least squares problem again is just finding the point in the subspace W that's closest to the vector V, right? But that just happens to be what's now called the vector projection onto the subspace. Right, so we want to project V onto a subspace. And so, so now, instead of just a single vector, we have to take an orthonormal basis for a subspace, right? So we have an orthonormal basis, but calculating this projection again is now just generalizing this calculation here, right? So that's V against W1 times W1 plus V against W2 times W2, and so on. Okay, so basically this calculation here is just trying to find the vector projection of V onto the subspace W, which tells us exactly the closest vector to V is and the closest vector minimizes this, which minimizes this least squares thing here. So that's basically where this calculation comes from, geometrically speaking.